If you had seen it like 50 times already, you would remember it, right? And the reference that I was making is to this, P plus NA over V squared, V minus NB is equal to nRT. Okay, in Chem 1A, I gave a problem where we had to solve for V. And then we came up with an equation. After you do the algebra and simplify it, we get AV cubed, right, plus BV squared, plus CV, plus D. It's a cubic equation. Is this bringing back memories or still not registering? Yeah. All right. And then what I was expecting is the people who remember this from Chem 1A remembered what a pain it was and that nobody solved this problem. Remember that? Nobody solved this problem in Chem 1A. Nobody. Even math majors didn't solve this problem. And so then, but so easy to forget. Yeah, that was one problem. Hopefully I'll never see it again. I'll never see it again. Don't ever have to worry about that again, and then I'll be happy and go on my way. But this is the reason why I say, a lot of people say, I got a calculator that does it. Well, you're going to be in for a surprise because science is full of math that's way too hard to solve. It's just, it starts with the Schrodinger equation. Most people remember the Schrodinger equation because the Schrodinger equation can only be solved exactly for the hydrogen atom. Anything more complicated than hydrogen has to be solved using approximations. But you go, well, there's supercomputers. A supercomputer can't solve that exactly? No. A supercomputer cannot solve that exactly. And so we have to do these approximations where we simulate the orbitals using mathematical functions. And depending on how many mathematical functions you use, this is why if you guys use Spartan, there's 3G, 6G, that's how many you're solving the Schrodinger equation using 3 mathematical functions, 3 Gaussian functions. 6G, 6 mathematical functions. The calculations get more complex from there. And so, this is it. If you remember, think about what advantage you would have had if you remember this from Chem 1A. How hard the cubic. You wouldn't have wasted any time factoring and getting into this form because once we got in this form, we did nothing with it, right? Instead, we would have left it in this, well, actually, we would have simplified this a little bit. We would have done 1.48 is equal to 4x cubed. That's as much simplification as I would do on this because it's just not worth doing anymore. And then just leave the bottom 0.200 minus 2x, 0.100 minus x. And so now we have this cubic equation and we go, now how do we solve this? So nobody remembers this? Then it's been effectively, totally wiped clean. You have vague recollections, Utama, of doing this? Just a little bit? Okay, how do we solve a problem like this, right? How we solve this is, it's very handy. It's in Appendix A. And it's called the method, okay, fill in the rest. Method, come on, somebody help me out here. Tell me at least one little pebble of memory is left or is completely gone. Completely gone. Wow, it's only last semester. 3 months ago when we covered chapter 6? 2 months ago? 3 months ago. Maybe longer. 4 months ago. Well, it wasn't that long ago. Method of yes. Method of successive approximations. Or, I saw that they're teaching this in elementary school now. The guess and check method. Right? This is the guess and check method. So all we do is we guess a value of x and then see, does it work? And so an example of the guess and check method would be something like this. 2x is equal to 6. If we didn't know how to solve this, we might guess x is equal to 2, right? If we guess x is equal to 2, then we get 4 is equal to 6. Well, that's wrong. And so we guess another. The x is too small. We guess x is equal to 2.5, then we get 5 is equal to 6. Well, that's still wrong. And then we guess x is equal to 3. If we guess 6 is equal to 6, and we're there. Right? That's the guess and check method. And so if you guys had this experience, this past experience, what are you supposed to do? You're not supposed to crack open the solutions guide. You're supposed to pound your head against the wall until it sinks in, right? How to solve this problem, right? How many hours would you have wasted on this? If you remember this experience, you would have wasted no time with algebra and went straight to guess and check, and in 10 minutes you should have had the answer. But you didn't, right? But now, the thing is, now you should think, well, some of those things, even though you don't see the application in the future, if you just drill those into your subconscious, then maybe it sticks and maybe you can use it. And the more times you see it, how do you know what values to put? Now, yeah, that's right. It seems like, I can guess a bunch of 300,400.0185. That's a guess. But there's only certain guesses that work. We aren't, could we have like Anthony was saying, could x be negative? And so if x were negative, we get negative molarity. If somebody said, I need to make a negative 1 molar sodium chloride, so can you weigh out negative x.xx grams of sodium chloride? Or you know what, I'm on a low sodium diet. I want you to give me negative 10 grams of sodium chloride, and then I'll be perfect. My sodium level will be,
Okay, so what my logic was, since you said everyone class, the comfort plus almost equal to the into plus, I just assumed that's a 0. Well, for the bottom part.
Okay, if you assume that's 0, then we end up with 0 and 0, right? But that's very far from our ratio. The ratio here of products to reactants should be 1.48. And so in the end, we have to have a ratio that matches this. And so it can't be 0. The stoichiometry I was talking about earlier is just for this line. It's a 2-to-1 ratio. And that's all. But if there was 0 change here, there's no reaction, that's not really the case, because let me get to that in just a second, because here we know that x is going to be bounded. X has to be greater than 0. It cannot be negative, right? And so x has got to be greater than 0, and it has to be less than what? Because we can't destroy atoms. It has to be less than 0.1, because how can we end up with negative molarity at the end? Let's say if x were 0.2, then we get 0.1 minus 0.2, which leaves us with negative 0.1 molar. It's impossible. And so we're just limited. We're limited between an x value between 0 and 0.1. Okay, the next thing is this k tells us information too, the magnitude of the k. The types of equations that we do in Chem 1a, let's look at the magnitude of the k. If k is greater than 10 to the 10, that's a huge number. It's like 10 billion. And so the way I think about this is this is approximately equal to the ratio of the products over the reactants. And so this is like having 10 billion parts of product to every one reactant. It's not perfectly the ratio because we get the square terms and all the other stuff that pop in there, right? But it's close enough. And so this tells us it's pretty much all product or all reactant. If you see a ratio this big, it tells you it's all product. And so this is the type of reaction we deal in Chem 1a. In Chem 1a, we would just do our normal stoichiometry. The reaction just goes forward. There's limiting reagents completely consumed. We end up with 0 left over. And so in other words, this is 100% forward reaction in Chem 1a. 100% reaction. However, in Chem 1b, if it's 10 billion to 1, we still want to know how much. Is it 1? Is it 0.5? What is it? And so in Chem 1b, we're going to do an ice, even though it's just a regular stoichiometry type problem in Chem 1a. And so Chem 1b, in Chem 1b, we do ice for everything. In Chem 1a, you get reactions that have K values less than 10 to the minus 10. If it has a K value less than 10 to the minus 10, it tells you 1 part product, 10 billion parts reactant, which pretty much says Did much reaction happen? Pretty much no reaction. So in Chem 1A, we call this no reaction. In Chem 1B, we want to know, if it's only 1 out of 10 billion, I want to know that. Or if it's 1 out of a trillion, I want to know that. And so in Chem 1B, we are going to do ice, even though, and so we're going to ignore how we did in Chem 1A, and we're going to do Chem 1B style. The problem is between these two. In Chem 1A, we never did anything between these. All the reactions with a K value between 10 to the 10 and about 10 to the minus 10, we said were partial. In other words, weak acids partially ionized, like acetic acid. Well, that's partial reaction. That partial reaction, we ignore that. We didn't do any stoichiometry. And so Chem 1A completely ignores this whole region here. But Chem 1B, we're going to do it because we have ice. We can just do an ice table like we're doing right now. And so this is the region where we ignore the reactions in Chem 1A. We just don't get reactions in this. And if we do, then we're doing it wrong, right? This is partial reaction. And so we think about this K value, and this is going to give us our first clue on how to guess X. Take a look at this K value. This K value is close to 1. If the K value is close to 1, what does it tell you? It's like a 1-to-1 ratio. If it's a 1-to-1 ratio, then I expect about half and half, right? And so what should you guess for your first X? I would guess my first X, I would guess, well, if I have 100 and I want a 50-50 at the end, then how much of this should I react? Half of it. So half of it would be 0.05. So then if I have 100 here and I get 0.05, I'm going to end up with 0.05 here, and I'm going to end up with 0.05 here, 50-50 mix, which is close to kind of what I expect here. And so I think the best guess here is guess an X of 0.05. I don't want too many digits, because the more digits I have here, the more headache it is to punch in the calculator. And so let's just use one digit here, 0.05. If I use 0.05, then 1.48 is equal to, and then you plug it in here. This would be 0.05 cubed times 4, and then this would be 2, so 0.2 minus 0.1 gives me 0.1 squared, and then this would be 0.05. Punch it in your calculator and see what number it comes out to. And let's see how far off we are from 1.48. One? Wow, that 1.0? 1.00? Wow, that's close. We were very, is that close enough? No, it's not close enough. We're close. Close, but not close enough. And so it's hot. And so should we make it a little bit bigger or a little bit smaller? So we look at this term, and it looks like the numerator increases faster than the denominator, so let's make it bigger. And so the next X I'm going to guess is, what? Okay, let's try 0.07. We'll make it a little bit bigger and then see if it comes out closer. And so plug in 0.07 in this equation and then see. And so our target is 1.48.
I got 12.7.
12.7. Too big, right? Too big. And so 0.07 was going too big. We need to bring it way closer to 1. And so I think 0.06 is going to be way too big. And so we're going to have to go one more decimal place over. So let's try 0.05 what? 0.055? All right, let's try 0.055 and see what that brings us. So let's make a little table, 0.055, and then we'll figure out what K is. K should equal 1.48. Let's see what we get here.
It's 1.8.
1.8? 1.8 is still too big. And so if we get, with 0.055 we get 1.8, and 0.05 we get 1.0, we want to go to 1.5 roughly. And so I would guess 0.053 because it's going to be on the higher side. You know, it's 5 parts out of 8. So what is 5/8? Let's closer to, let's go to 0.053. No, it's more than halfway.
Uh,
1.43. Oh, a little bit too small. But is that close enough? I mean, it's supposed to be 1.48. We get 1.43. Is that close enough? No, it's not close enough. And so we just need to go a little bit higher. 0.05, 0.054 would be too high. And so let's go 0.053. 1? All right, let's try 0.0531. No, not let's, I'll let you do all the work. I'll just copy down the answer. One point 45, still too small. 0.053, 3 or 2? What do you want to do? 3.3, 3.2, 3.3. All right. Do it. 1.486. Ooh. 1.486, not good enough because 1.486 rounds to 1.49. Too high. So I think we should have gone with a 2, huh? 0.0532. Come out 2. Ooh. 1.468 is too low. That rounds to 1.47. We're so close, but it's not good enough. What are we going to do? 0.05325. Halfway, okay. Halfway sounds, you know, roughly right. Maybe 4, you know, because it's a little less than halfway between those two. So I probably would have gone 4, but let's go with 5 since we already said 5. What do you get? I'd still probably. Do you see, if this were 68 to 88, that would be halfway. But it's all right. Let's try this.
1.477.
1.477. Is that close enough?
Yeah.
Yeah. All right, when do you know when to stop? There are two places where you stop. One is where the number you're calculating rounds to the correct number of sig figs. And so this is fine. 1.477 rounds to 1.48, we're good. Or two, you're getting so many decimal places that, you know, you gotta round those anyway. How many decimal places are we allowed? You know, in the subtraction, how many decimal places are we allowed? Only 3. Now we're up to 5. 1, 2, 3, 5 decimal. That's more. We're going to have to round those extra digits anyway, right? Round them off at the end. But we don't want to do any premature rounding. And so we always like to carry extra digits. I'll tell you why we like to carry extra digits in a minute. But, you know, think about that. If you knew what to do and you had done this before, then 10 minutes would have been perfectly adequate to figure it out, right? But if you've never done this before, and you've never seen this before, and you've never even heard of successive approximations, then would you have ever figured it out, no matter how much time you would have spent? Because you would have been trying to solve it algebraically by factoring or by doing whatever else, and you would have never gotten the answer. And all the people, and things are graded on the curve, all the people who got the answer are going to get the 100%. All the people who had struggled, and there's some professors at UCs that give 0 partial credit, would have gotten 0 for all that work, you know? Not all the professors are that harsh, but there are some. But anyway, so this is the tremendous advantage if you just recalled, you know, the terrible experience that you had with the van der Waals equation in the past, right? But anyway. Okay, so I just wanted you to solve for x. Now we're going to do the rest. What we're going to do is now we have enough information to calculate the equilibrium concentrations here. And so the way we set this up is, since addition and subtraction, you're looking at the decimal places, we just line it up like this. And so I need to do 2x, so I need to double this. So this is our x value here. 0.05325. So I'm going to double this. This is going to give me 0.165. 0.10650. I'm allowed 4 there. But the 0, you know, I'm gonna just drop it to keep the math simpler. Just do that. So we'll carry an extra 0 here. If there are more digits out here, I'd carry them. And so that's gonna give me 5, which I'm gonna subscript 9. That's gonna give me 3. And this is going to be 0.09. So 0.0935 molar. Okay, this one's going to be 0.100 minus x. So we'll just use that as is, 0.05325. I need a couple of extra zeros there. So this is going to give me 5927. It's going to give me 6, 4, 0.046. So how much reaction did we have? We started off with 100 and we lost 53.25%. So we had 53.25% reaction. This is stoichiometric, so it's going to be the same. This is 0.200, we lost double that, and so this is still 53. So we have about 53% reaction. Is that the same percent reaction that we saw in experiments 1, 2, and 3? No, it's a different percent. All right, so 2x over here, this is just going to be 0.1065 molar, and x is 0.05325 molar. I'm not actually allowed that many sig figs because the point of 1.48. And so let's just round to the correct 3 sig figs. And this is what I'm going to round to the correct decimal place here. And so I get about 53% reaction, and then it stops reacting. Well, does it really stop reacting? No, it continues to react, but we hit this situation where we got a dynamic equilibrium. Where, you know, as soon as I make the extra product reacts in the reverse reaction, and then, you know, we get the reaction. It's constantly reacting, but these concentrations no longer change because the forward reaction rate is equal to the reverse reaction rate, and we see no net macroscopic change. And so this is a Chem 1B stoichiometry problem. This is it. This is our answer, right? After this, how much limiting reaction? Well, there's no limiting reaction in this case, but you know, we got reactants that are left over in some product form. And that's what's going to happen. Okay, we're not done yet, though. And something we always do with these ice problems, and that is we always double check our answer. How can I double check my answer? And the way I double check it is I have my equilibrium concentrations here. And I know that the ratio of equilibrium concentrations here has to equal 1.48. And so the way I double check this, although this might be redundant because of the successive approximations, but we don't always use successive approximations to solve every problem. And so when we double check this, I'm just going to plug the concentrations back in here and see if I get the 1.48 ratio. And so 1.48 should equal, now it's going to be the copper 2 concentration, so that's 0.0165, and I need to square that. So that's my copper 2 concentration. But a lot of people get mixed up here because they say, shouldn't I take this and double it? In other words, it's 1065, so I should double this, right? Because I need 2. Is that right? No, it's wrong. You know, it doesn't matter what I have here. This is just the ratio in which the copper and the tin react. It has nothing to do with that. And the doubling comes from the X part anyway, here. And so this is the concentration of copper 2 plus. That's what I put in here. The concentration of tin 4 is 0.053225. The concentration of copper 2 is 0.0935 squared. The concentration of tin 2 is 0.04675. And so, can somebody double check this? See what it comes out to? This is just to make sure we didn't make any errors. What does it come out to? 1.477? As we expected, 1.477, which rounds to 1.48. So it's good, right? The thing is, people introduce error all the time, you know, maybe unintentionally, maybe intentionally, I don't know, but they introduce error all the time. You know how they introduce error? They love to round everything. Rounding everything leads to round-off errors, which can be quite significant. And so I want you to repeat this calculation here. Repeat this calculation, but let's round these concentrations. And so rather than using 0.1065, let's round this to 107. And so do 0.107 squared divided by 0.0533 divided by 0.094 squared divided by 0.047 raise the first. And so we repeat the K calculation, but this time round with the rounded concentrations. And what does the calculation come out to? .46. Now the problem is this. Although this came out close, is that error due to round off, or is that error due to a calculation error? It's due to round off. But the people who like to round off everything, they don't know. And so they have to go back and double check all their calculations. And so what we do is we always carry extra digits in our ICE calculation so that when we do our double check, then we can eliminate the possibility of round off error. Because sometimes round off error can lead to, up to 10% errors, 10% differences. And then if you see a 10% difference, you're going, man, my calculation's way off. Well, is it way off just because you're rounding everything, or is it way off because you actually did an error? And so we like to carry extra digits, always. But there's a problem, there's one additional problem. How many digits does your calculator carry? Do you know? How many digits does your calculator carry before it rounds the number? Nine? You have 9 digits? 9, my calculator is like 8 digits, my old calculator is 8 digits, my new calculator is 10 digits. Excel, how many digits? Maybe hundreds of digits. Right? And so some people say, yeah, I don't have to worry about rounding. I can always use Excel. Just bring my laptop, open up Excel, then I don't have to worry about my calculator not giving me the correct answer, because what happens is this. Are we good with this calculation? You have to learn little tricks. One of the tricks you have to learn is successive approximations, because the calculations get quite difficult. Another trick you have to learn is how your calculator deals with rounding, right? Because let's say you had a situation like this. Your initial was 0.200, and your change was this, 19999. So let's say your calculator carried 8 or 10. Let's say your calculator carries 10 digits. And so if this were the change, what would your calculator round this to? Can your calculator carry that many? Try it. It's 0.1, and let's see how many nines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So put in a 0.1 and then put 11 nines after that, and then hit equals or enter. And what does it come out to? It comes out to 0.2. And so your calculator is automatically going to round this to 0.2. And so that means the change is 0.2 because your calculator can't help. Well, you could say, I always got Excel. I could do this on Excel, right? Use a computer, use a laptop. I don't need to learn these little tricks, mathematical tricks, because I'll just use Excel. And when Excel runs out, well, I'll just borrow a supercomputer or something, somebody, or Mathematica or something like that. Because what you're going to get at the end is 0 molar. And then you go, okay, now I'm going to do my double check. I'm going to do my double check, and when you do your double check, you get all this stuff divided by 0. And then you get, oh, my K is infinity. Well, the K was supposed to be, let's say the K was supposed to be 1.3 times 10 to the 6 or something like that. That's their K value. What is the percent error that you just got? So you got infinity. It's supposed to be 1.3 times 10 to the 6. What is the percent error? Infinity. And so, you know how many people get infinite percent errors? A lot. A lot, because they don't, they just go with the flow, and the flow leads them down over the waterfall to a, and so, so I have a choice. I have a choice. I could say, well, maybe that's not a fair problem. It's not a fair problem because most people don't have Excel, And so maybe I'll avoid problems like this where your calculator automatically rounds it and gives you some ridiculous answer. And maybe I should do that. But that requires me thinking about this and purposely trying to avoid problems like this that might come up, right? But I'm not going to do that. You might encounter a problem that you get some nonsensical answer and you have to come up with a trick to, well, the trick is actually very easy. The problem is that I get so much resistance because the trick is not necessarily explicitly stated in the textbook and this and that, and so it's not fair, this and that, or it's too hard. Well, too hard, it's not hard, it's very easy. And so we're going to learn the trick on the next example, because, okay, so successive approximations is one trick you should have up your sleeve, right, to solve problems like this quickly, because remember I said there's a lot of time pressure, and who's going to win all the points? The people who are fast, not the people who are just thinking, well, how do especially since things are graded on a curve. If this were graded on a curve and one person in the class got it right and everybody else got it wrong, then that curve is going to be bimodal. One passed, everybody else failed. We see bimodal curves all the time at UC. The distribution is very weird. And you better believe there's some pre-med student, not just one, but a bunch that are going to get it. Because their whole life since they were in kindergarten has been devoted to becoming some neurosurgeon or something like that. Or, it's true, I've read it, in the essays, since I was or something. So some guys, the girl is going to get it. Anyway, let's see. Not all of these problems are going to be this tricky. But let's take a look at another one. And I forgot my book. It's all right. Okay. So, what kind of reaction is this? Well, one way I would have looked at this and I would have said, hey, what kind of reaction this is? This is a metathesis reaction. What should I form in this metathesis reaction? Well, let me write it over here. Copper 2 plus, do you recognize this as a metathesis reaction? It would be Cu2 plus plus. You might even be able to balance it in your head when you write it down. It would be 2NH3 plus 2H2O liquid gives me solid plus driving force, precipitation of the copper 2 hydroxide. But did you know if you put in excess ammonia, this is a reaction that some of you did in Chem 1A. In Chem 1A, in experiment 18, you take some copper wire and you mix it with bromine water. And then the product of that solution you divide into 2 test tubes. One test tube you add silver nitrate, white PBT. The other test tube you add aqueous ammonia. Now if you watch the aqueous ammonia, what happens is, I should have just brought this in, show you, because you probably don't remember it. You remember what I'm talking about? You remember it, man? Okay, as you add the aqueous ammonia, initially you get a very light blue, baby blue precipitate. And then as you keep adding the aqueous ammonia, that blue precipitate disappears and is replaced by deep blue solution. Anybody remember that? Yeah, kind of. Yeah, it's a very pretty light blue precipitate and then it vanishes. You go, where did my precipitate go? Well, this is what happens. Initially you form the precipitate, but if you keep adding ammonia, what happens is this, the copper 2 ends up getting attacked in the precipitate. And overall what happens is the copper 2 gets attacked and forms this. How would you name this ion that is formed? Tetramine copper 2 ion. This is very deep blue. This is a light blue color. Sometimes it's even hard to see it. But if it's concentrated enough, you can see it. But once you add that ammonia and a lot of it, initially you add the ammonia, you get that precipitate, and then you add a lot more ammonia, and you end up with this. We're going to talk about this a lot more in chapter 18. But right now, we're just going to do a simple ICE calculation. And let's see what the K value is for this. I need to grab the K value for this. But I'll bring it up. So let's do the table first. This is what I'm going to do for the table. Initially, I'm going to make this 0.100 molar. You know what? I'm going to make this 0.100 molar. I'm going to make this non-stoichiometric. You know what I'm going to do? I'm going to make this. What ammonia did we use? I think we used 6.00 molar ammonia, or 3 molar. I can't remember if it's 3 or 6. Probably 6 molar. Sometimes we use higher concentration, 12 or 16 molar ammonia. And 0 molar here. In Chem 1A, this would be easy, right? In Chem 1A, we just say, hey, this is limiting reagent, excess reagent problem. Limiting reagent here is copper 2. Copper 2's limiting reagent is always completely consumed, so we go to 0, and then we figure out how much excess reagent was consumed. You know? And then we should end up with 0.100 molar. Very simple Chem 1A style stoichiometry problem. Right? Oh, the computer's on, so let me just bring this out, because otherwise I'd have to run to my office. I forgot to bring in the I'll just get it off Wikipedia or something, which might be a little bit different than our book, you know, depending on the date. Um, 3.1 times 10 to the 1.1 times. Looks like it's 1.1 times 10 to the 13. This is 5.6 times 10 to the 11, but I think I remember it being 10 to the 13, so we'll just use that. We published in 2009, so this is probably all right. 1.1 times 10 to the 13, which would have been fine. In Chem 1A, you know, because look at that K value. What does that K value tell you? It's a huge number, which means it's all product. And so this is one we would have done stoichiometrically in Chem 1A and come out with it. But you know, in Chem 1B, we want to know what that little bit that's left over. How much is that little bit that's left over? We want to know that. And so this is why we're going to do a Chem 1B style calculation for this. All right, so why don't you go ahead and start this, right? And tell me what that little bit that's left over is going to be. Tell me how much that's going to be, okay?